AP problem number 1. Okay, part A is asking us to find the empirical formula of the gas, including hydrogen and fluorine. So we know that 95% of the gas is composed of fluorine, so we take the percent and we convert it to mass in grams, and then we find the molar conversion of it. There's 19 grams of fluorine in a typical atom, and that's equivalent to 1 mole. 95 divided by 19 is equal to 5 moles, and just forget that part, we'll get to it, don't worry about it. And since we know that 95% of the compound is fluorine, that means that 5% is composed of hydrogen. So 5% convert to grams, that's all good. The molar conversion for hydrogen is 1.01 grams per mole. 5 divided by 1.01 grams is equal to 4.95. And the way to find out the coefficients, if there are any, for an empirical formula is to find the limiting reactant of the compound, which in this case is hydrogen because 4.95 is less than 5, and divide each of the moles by the limiting reactant value. And for hydrogen, 4.95 divided by 4.95, which is equal to 1, and 5 divided by 4.95 is close enough to 1 that we can just say it's 1. No one's paying attention. And so therefore we get this as our empirical formula for the gas compound. So part B is a little bit different. We are asked to find the fraction of fluorine in both the solid and gaseous compounds that it's in. So first we start off with the uranium fluoride compound. So we know that 1 mole of uranium fluoride is equal to 352.03 grams of that compound. And this is how much we're given of it in the problem, just 4.267 grams. And from there, so that would put us at the molar conversion like we were doing in part A. But to find the fluorine and to get it equivalent to the fluorine so we can really work with it, we have to do another a molar ratio. For every 1 mole of uranium fluoride, there's 6 moles of fluoride. There shouldn't be a 6 here. Get rid of that. That's fine. And all that 4.267 divided by 352.03 grams times 6 is equal to 0.07273 moles of fluorine. So that's the solid compound, but we're not done with that yet. We have to find the percent of it. So moving on to the gaseous compound, we are given 0.97 grams of the gas. So that's our given, but we know that the molar mass of that compound is 20 grams, and it's 20 grams per 1 mole. And from there, we do another molar ratio. For every 1 mole of the gas, there's 1 mole of fluorine. So that all together, 0.97 divided by 20 times 1 is equal to 0.0485 moles of fluorine. So we know that, and that's all good. So now we can take the percent of it. So this was how much was in the how much of fluorine was in the compound initially before it reacted to form a gas. So we have the value of the gas up here, 0.0485 moles, and then we're going to divide it by the initial amount of fluorine, so 0.07273 moles, and that puts us at 66.6, right? Ooh, hold on. Which one does it do? Yeah, I was right. Okay, we're good. That is equivalent to 8 moles of fluorine, and times 100, that would be our percent, so that's 66.68% of fluorine, and that's in the solid compound. But wait, what about the gas compound? Oh my gosh. We know that we can't like have let me start over. We know that 0.6668 has a counterpart that would equal make it equal to 100 or 1.0 in terms of decimals. So if we subtract 0.6668 from 1, we get 0.3332. So we also multiply that by 100 to get a percent, and that is 33.32%, and that is the amount of the percent of fluorine in the gas compound. So part C is asking for the formula of the precipitate. So this is pretty much just going to be like finding the empirical formula of a compound. So first I started off by finding the moles of water that we have in the solution, or the grams of water rather, I'm sorry. So we took the amount of the uranium fluoride compound that we were given, and this is representing the reactant side of the equation, this is representing the product side of the equation, and we know that the total mass of that is the uranium fluoride compound plus water, and we don't know how much water we were given, so we have to solve for it. But we know on the product side that we were given 0.97 grams of the gaseous compound and 3.73 of the 3.73 grams of the precipitate. So adding those together and then subtracting 4.267 from that side, we get that X, or the H2O, is equal to 0.433 grams. And then that's all good, but we don't need that to figure out, we don't need H2O specifically to figure out the precipitate. We need to find what that is equivalent to in terms of moles of oxygen. So we have the value that we just solved for divided by 18.0, which is the typical molar mass of water, and that's it's 18 grams per 1 mole. And then we have another molar ratio. 1 mole of oxygen was equal to 1 mole of H2O, so that's perfect. 0.433 divided by 18 was equal to 0.02406 moles of oxygen, and I have them all written out later. Then for fluorine, this was the amount of fluorine that was in oh my gosh, I'm sorry. Oh, that was the amount that was in the solid compound, which is up here. That was on the reactant side. And then we found that in the gaseous compound, there was 0.0485 moles of fluorine there. So subtracting that from that, we get 0.02433 moles of fluorine. Ooh, oh my gosh. So there's that. Now uranium. So it's pretty safe to assume that uranium is going to be our limiting reactant just looking at it, because fluorine and hydrogen and oxygen are all elements that are commonly found, but when are you going to find uranium ever just out and about? So 4.267 grams of uranium fluoride, that's just our given again, divided by the molar mass of uranium fluoride, 352, and then to a molar ratio, that's a sad U, 1 mole of uranium is equal to 1 mole of uranium fluoride. That's just how the coefficients were set up. So 4.267 divided by 352 grams is equal to 0.01212 moles of uranium. So over here, this is all the things we just solved for. Uranium, fluoride, sorry, it's sketchy, and oxygen. So it's like solving for an empirical formula. You would take the limiting reactant and divide it by, and divide it into all of the other reactants. So 0.01212 divided by 0.01212 is equal to 1. For fluorine, 0.02433 divided by 0.01212, this is a mouthful, is equal to 2. So that's going to be our subscript for that. And lastly, oxygen, 0.0241 divided by 0.01212 is equal to 2 as well, or approximately equal to 2. No one's checking. And that gives us our precipitate. So we have the no subscript over here. It's equal to 1. You don't have to write 1. The 2's are over there, and that's it for part C. And I wrote part D. Ooh, get in focus. I wrote part D on a separate sheet of paper because it was getting way too crowded in there. But part D was just asking us to balance out the formula. So we have our reactant side. There we go. Hello. Uranium fluoride, water, our precipitate, and hydrogen, the gaseous compound. So I didn't put the coefficients in. I figured it would just be easier to show my reasoning throughout this. So, starting with that, let's go. Oh, okay, I can see it already. Hold on. So for fluorine, there's 6 of them over here. We're missing 4 over here. There's only 2 on the product side. So what we can do here, let me not look at the camera and look at the actual paper, is put a coefficient in front of the gaseous compound. So then there's 4 fluorines, and then plus 2 is equal to 6. Uranium, we don't have to worry about it. There's 1 and 1. We're good. Now there's 4 hydrogens over here. What's up with that? So we'll have to put 2 in front of the water. So now we have 2 hydrogens. What about oxygen? Oxygen, we have 2 over here, and we have 2 over here, and it all checks out. So in the end, part D, coefficient of 1, or we don't have to write anything, coefficient of 2, 1, and 4. Yay! I finally did it.